Hi guys! In this video, we're going to be discussing power of a point and radical axes. We're going to be starting off by looking at power of a point once again, and we'll use power of a point to look more into radical axes. Radical axes have profound applications such as the radical center theorem, and we'll see how to apply that in examples. Alright, so first, let's review power of a point. So it all starts with a circle here. So suppose we have points A, B, C, and D on it, and they're in that order. You probably know about power of a point, that if AC and BD intersect this point E here, then EA times EC is equal to EB times ED. And the proof of this is just using similar triangles. Because if you draw these two lines, then you end up getting that triangle EAB is actually oppositely similar to triangle EDC. And with that, we can just use the fact that the lengths have equal ratios. So AE to ED equals BE over EC, and that gives the power of a point theorem. And we can also use power of a point when the point intersection lies outside of the quadrilateral. So let me go ahead and relabel things. So this is point B here, and then this is point C, and this is point D, and these guys intersect at a point E out here. Then EA times ED is equal to EB times EC. And this is power of a point. All right, so it seems like power of a point is really powerful, and in fact, the converse holds true. But this is sadly not true in general when we only look at these normal lengths. Because, for example, consider what happens in this case. Suppose that we have a point E here, and this is A, this is C, and this is B, and this is D. And this can be 2, 2, 1, and then this is 4. Then EA times EC is equal to 4, and so is EEB times ED. However, these points are clearly not cyclic, so it seems like the power of a point converse is not true. To overcome this, we use directed lengths. What is a directed length, you may ask? Well, consider we have points X and Z on this line. And suppose we have a point Y here. Then consider the lengths YX and YZ. The length YX goes in this direction from Y to X, while the length YZ goes in this direction from Y to Z. So because they're in different directions, we say that they have opposite signs. So that means that YX, for example, could be positive and YZ would be negative. And by this logic, we would also have that XZ is negative because XZ goes in the same direction as YZ. So XZ and YZ have the same direction and same sign, therefore. And the ZX has positive sign. In general, XY is equal to the length negative YX. So XY equals negative YX with directed lengths instead of them being equal to each other. So again, we have that ZY is also positive, and so is YX, as I said earlier. And again, XY is negative. So we have all of these signs here. So what you may ask is, why do directed lengths even matter? Well, it turns out that if we use directed lengths, the power of a point converse holds. And here's how. Suppose we have points A, B, C, and D here, or I'll make it C, D, and C. And suppose that they intersect at this point E here. Then if EA times EB is equal to ED times EC in directed lengths, If this is true in directed lengths, then the points A, B, C, and D are concyclic. Sorry, that's a bad circle. It should be something like that, I guess. So you have that if we direct the lengths, then the power of a point converse holds. So if and only if A, B, C, D cyclic. And the good thing about directed lengths is that it allows us to go inside the circle as well. So if we have this as well here, so A, C, B, and D, then this product here is negative when it's inside the circle because EA and EC have different signs when E is inside the circle because they're going in different directions. So therefore the power of E is negative in this circle, while in here the power is positive. In fact, with this notion of points outside and inside the circle with the power being positive or negative, we can state a more general form of power of a point as follows. Suppose we have a circle. Here's a circle. And a point X outside of it. Then for every single line passing through X that intersects a circle, suppose at A and B, the directed length quantity XA times XB is always equal to a constant as A and B move, such that AB passes through X. And if X lies outside of the circle, then this quantity is positive because XA and XB point in the same direction. And if it's inside the circle, like this point Y here, then it's negative because YA and YB face in the opposite directions. So this is a nice generalization of power of a point. And we can actually calculate explicitly what the power is equal to. For example, when we have a point X here, so again, we have our circle and the point X. If we have the center and the radius is equal to R, it turns out that the power with respect to this circle omega of X is equal to OX squared minus R squared. For any point X, it can be inside the circle or outside the circle. And exercise for you guys is to prove this. This shouldn't be too complicated because try thinking of a certain line that passes through X. That will make it easier to deal with. That introduces the center. All right. So with power of a point introduced, we can now move on to radical axes. Now at some point you might have noticed that if we have two circles instead of one, so we have two of these circles here and they intersect at P and Q, then any point on this line PQ has equal power with respect to each circle. So we have a point X here. Then the power of, this is omega 1, this is omega 2, then the power of, with respect to omega 1 of X is equal to XP times XQ. But this is also the same as power with respect to omega 2 of X. So the natural question arises, are there any other points X which satisfy this property? Well, with this, we can introduce a set of points that satisfy this property, and it is called the radical axis of the two circles. Basically, the radical axis is a set of points X such that the power from X to each circle is the same. So power with respect to omega 1 of X is equal to power with respect to omega 2 of X. So, for example, the radical axis consists of all the points on the line PQ in this example. And if we have a point X out here, then this is not on the radical axis because the power with respect to omega 1 and omega 2 here are not the same. And do the circles need to intersect in order to have a radical axis? Absolutely not. For example, if we have a circle like this and a circle like this here, then the radical axis would be a line like this. Even though the circles don't intersect at all, they still have a radical axis. and this point has equal power with respect to each circle. All right, you may be asking, what is so special about this radical axis? This radical axis could be just this line here, or it could be just a bunch of other stuff. Like it could be a point over here, a point over here. Nope, not at all. As it turns out, the radical axis is always a line, and I want to emphasize this. So if we have any two circles, the radical axis is always a line. And this is really, really, really important. So naturally, we may want to prove it. So let me go ahead and erase everything. So how do we prove this? Well, there's no really nice way to deal with powers arbitrarily. So this is where we can use a bashing technique called Cartesian coordinates that you might have heard of in school. And basically, we just put the circles in the coordinate plane. So we can assume that one of the circles is centered at the origin because we can just translate it. And by rotating the diagram, we can assume that the other circle lies on the x-axis as well. It centers on the x-axis. So suppose that this circle is centered at 0, 0 and has radius r. And this circle is centered at 0, s and has radius t. Then the equation of this circle here is equal to x squared plus y squared is equal to r squared. And this one here is x minus s squared plus y minus t squared is, no, it's y plus y squared, my bad, is equal to t squared. So now, suppose we have a point x that lies on the radical axis. What is the power of x with respect to this first circle? Well, the distance from x, which I'll call xy, to the first circle squared is x squared plus y squared. And the radius squared is just r squared. So we again get x squared plus y squared minus r squared. And that's the power of x with respect to the first circle. And for the second circle, the distance from x to the center of the second one is just x minus s squared plus y squared. And we subtract out the square of the radius, and that's t squared. So therefore, the radical axis consists of all the points which satisfy this property. And conveniently, the y squareds cancel out. And if we expand this guy here, we get x squared minus r squared is equal to x minus s squared minus t squared. And this is x squared minus 2x s plus s squared minus t squared. And these guys cancel out. And what do you know? We get a linear equation that we can solve for x. And therefore, x has a specific value, and which means that the radical axis is a line perpendicular to the line through the centers. And what if the circles intersect each other? Then if the circles intersect each other, because the radical axis is a line, we know that if it contains 2 points, then that's just the radical axis. So we have this, and the circles intersect at P and Q. Then we know that P and Q both lie on the radical axis. How come? Because we know that the power with respect to the first circle of P is equal to 0. And the same holds for the second circle, because P lies on the circle. Therefore, we have that P lies on the radical axis, and so does Q, which means that this line here is exactly the radical axis. So now that we've explored radical axis, let's take a look at a quick example. So here's our first example. Suppose that omega 1 and omega 2 are two circles which don't intersect, and such that one is not contained in the other. Prove that the midpoints of the common external tangents are collinear with the midpoints of the common internal tangents. In other words, all of these midpoints lie on the same line. So the first step in any geometry problem is to draw the diagram. And again, I'm going to ask you to draw the diagram on your own because it's good practice. So assuming you've drawn the diagram already, let's solve the problem. I'll draw a diagram here as well for my reference. So we have our two circles, omega 1 and omega 2, and we have our external tangents and our internal tangents. And we have our midpoints. This is one midpoint, this is another, another. And we want to prove that they all are collinear. So how can we prove that they're all collinear? Well, we want to use this fact that they're tangents somehow. So if we call this point x, we can say something special about the tangents. That if we call this a and this is b, then because x is a midpoint, we know that xa equals xb. So we already know this by default. So what else can we say? Well, for one, we can square both sides to get xa squared equals xb squared. You might be asking why we're doing this since it doesn't seem like we're doing anything at all. But however, the cool thing is that the power with respect to omega 1 of x, because x is a tangent, xa is a tangent. This is a very common technique when working with tangents, by the way, is that the power of point x is just the square of the tangent. And this means that xa squared is a power with respect to omega 1, and the power with respect to omega 2 is equal to xb squared. Which means that these two quantities are equal, so x lies on radical axis. But wait, if we repeat this logic for all of the other midpoints, we see that all of these midpoints also lie on the radical axis, which means that all of these midpoints are collinear on the radical axis of these two circles. And this finishes the problem. So the point is that you should always look out for the radical axis whenever you can. This is one of the more simple applications of radical axis, and this should hopefully demonstrate to you why it's so useful. We'll see one of the main theorems that we use involving it in a bit. So here's how we apply radical axes. Suppose that we have not one, not two, but three circles. And we have this one, and this one. I'm making them intersect for now because it will make the point I want to make clear. Then suppose that we look at their pairwise radical axes. So this is one radical axis. So here's one, here's another, and here's the third. And we see they all are concurrent at this one point here. In other words, the common chords of three pairwise intersecting circles seem to be concurrent. Why is this the case? Well, we can figure out why this is the case by using radical axes. So first, let's focus on two of the circles. And I'll call those omega 1 and omega 2. And we look at its radical axis. This radical axis we know is equal to the set of points x such that the power with respect to omega 1 of x is equal to the power with respect to omega 2 of x. And if we introduce a third circle and draw in this radical axis, and let this intersection here be z, then we know that z lies on the first radical axis, so the first two powers are equal. But z also lies on the second radical axis, which means that the power with respect to omega 3 of z is equal to the power with respect to omega 1 of z, by definition. So therefore, all of these three powers are equal. So what if we just replace omega 1 with omega 2 in this, because they're the same? So we have omega 3 and omega 2, and the powers with respect of z with respect to each circle is the same, which means that z lies on the third radical axis. And this proves that all three radical axes, the pairwise ones, are concurrent at a point z, called the radical center of the circle. And for this reason, this theorem is called the radical center theorem. And this is the main application of radical axis that we will use. And to see why this solves the other problem about the intersecting chords, that's because their pairwise radical axes are just their chords. So if we have this, this, and this, then one radical axis is this line here, the other one is this line here, and the third one is this line here, which I should have drawn better, but okay. So now we know that all three radical axes are concurrent, and this is a nice way to prove that three lines are concurrent, or otherwise 3 points are collinear. To see this, let's look at our second example. So suppose that we have our triangle ABC, and we have our altitudes D, E, and F. So AD, BE, and CF are altitudes. So D, E, and F. And we know that they concur at the orthocenter H. In other words, these altitudes all have the same point H in common. But we've never really bothered proving this properly. And in this video, we're going to be finally proving this using radical axes. There exists ways to prove it without radical axes, but I think this is a really instructive proof. Anyways, so we first know that we have all these right angles here. So right angle, right angle, right angle, right angle. So with all of these right angles, we end up getting that BFEC is cyclic. And similarly, we have AFDC cyclic, and then AEDB cyclic. Okay, so now that we know that all of these are cyclic, let's try drawing them in circles. In general, whenever you have a cyclic quadrilateral, always draw in the circle. Drawing in the circle for a cyclic quadrilateral will both help you to remember that the quadrilateral is cyclic, and also to remember that you can use radical axis with it. So let's draw in this circle here, and so this one here. Wait, let me draw it a bit better. And this one here. And as we know, they both intersect at points A and D because we have A and D and then A and D. So the radical axis of these two circles is just the line AD. And if we introduce this here as well, then the radical axis of these two circles here is the line BE, and the radical axis of these two is the line CF. So that means that AD is a radical axis, as are BE and CF. So what does this mean about them? Well, now we can apply the radical center theorem. And by the radical center theorem, they all have a common point at the radical center. And this is just the point H, and we just finished the problem. There's a related problem for you to try in the exercises, and I highly suggest doing that one. See if you can identify which one it is. All right, so now that we've explored radical center and radical axes, let's take a look at some applications of them. So our first application of radical axes is a concept called coaxial circles. Okay, so what exactly are coaxial circles? Well, a corollary of radical axes is that if we have three circles here that all share this point P here, then what happens if they share another point Q down here? Well, then this means that they all have the same radical axis, because then any point on PQ has the same power with respect to each circle. And this is our common radical axis. So let's call it omega 1, omega 2, omega 3. Nope, this should be omega 2 and this is omega 3. So all of these three circles have the same radical axis if they meet at another point Q. But what happens if they have the same radical axis? Does having the same radical axis imply that they share a common point? Well, let's see if we can prove this. So suppose that we have omega 1, omega 2 here, and they intersect at another point Q. And PQ is the radical axis of these two circles. Suppose that PQ is the radical axis of another circle with omega 1, say omega 3. So omega 3, and the radical axis of these two circles is the same. Then we know that this point here, consider this point here, must lie on the radical axis of omega 1 and omega 2, and also the radical axis of omega 1 and omega 3. So this means that the power with respect to omega 1 of Q is equal to the power with respect to omega 3 of Q. Because by definition, Q, which is over here, lies on the radical axis of omega 1 and omega 3. Because because PQ is a radical axis. But however, Q lies on the circle omega 3, which means that this power is equal to 0. So the power of Q with respect to omega 1 is equal to 0, which means that Q lies on omega 1. And the only way for this to happen is if the three circles have a common point. So to reiterate, we have the following theorem. So let me go ahead and erase this. So if omega 1, omega 2, and omega 3 are circles that have common point P, then they have the same radical axis if and only if they have a second intersection point. And this is very powerful in its own right, because it allows us to show that three circles have a second intersection point besides one very obvious one. And in general, it can also be used to prove that three circles intersect at two distinct points. And this is a slightly harder application of that. And there are some problems in the examples for you to try that involve using coaxial circles. Our second application should be a reasonably motivated idea, but in my opinion, it's extremely cool. So, have you ever tried drawing a circle when you were younger? That's so small, we just keep drawing smaller and smaller and smaller until it just becomes a point. In fact, the circle is just that point. This is the notion of a circle with radius 0. And the circle of radius 0, well, is just a point. So how are circles of radius 0 even helpful? Well, with radical axes, it helps to try using circles of radius 0 in radical center or radical axes. So let's look at one example. So suppose we have points A, B, and C. What happens if we use the radical center theorem on the circles with radius 0 centered at A? So like here, B over here, and C over here. Well, the radical axis of B and C, here the circles are radius 0. If a point X lies on this radical axis, then we know that xb squared minus the radius squared, which is just 0, is equal to xc squared, again minus the radius squared, which is 0. So xb equals xc. In other words, the radical axis of these two circles is just the perpendicular bisector. So we have that. And we also have the other perpendicular bisectors. So by radical center theorem, all of these perpendicular bisectors are concurrent at this center point O. And therefore, radical axes once again prove the existence of an essential triangle center, and this time being the circumcenter. But this is a pretty trivial example of circles of radius 0. So let's see if we can figure out some of their more general properties, because they seem really, really cool. So suppose we have a point A here, that's a circle of radius 0, and we have a circle omega out here. Then what is exactly the radical axis of these two circles I meant? Then suppose that we have this radical axis here, and it consists of a point x down here. Then we know that the power with respect to x of a, so the power with respect to a of x is equal to xa squared. So xa squared is equal to, and then we draw a tangent here, and that gives us the power with respect to omega of x. So that's xt squared. In other words, xa is equal to xt. In other words, the set of all points x such that xa is equal to xt as shown here is literally just a line. And if we want to further classify this line, we can do it as follows. Because in the case where a, x, and t all lie on the same line, then it becomes rather nice. So we have a here, this is t, and this is x. Then that means that x is the midpoint of AT. And we can also construct this other tangent u. So therefore, the radical axis of the circle with radius 0 centered at A and this circle omega here is just this midline here, the line connecting the midpoints of AT and AU. And you'll see an application of this in the examples. I'm not going to tell you which exercise this involves, but if you see it, you see it. And I think it's rather instructive. So here's our example problem. So we have that H is the orthocenter of an acute triangle ABC, and the circle gamma A centered at the midpoint of BC and passing through H intersects the sideline BC at points A1, A2, and the other points B1, B2, C1, and C2 are defined similarly. We wish to prove that all 6 of these points are concyclic. All right, so please try this problem on your own first and try your best to solve it. Go ahead and pause the video right now and try solving it. I'm going to be discussing the problem after you try it. So pause the video right now and go try it. Okay, so hopefully you've tried the problem by now. So let's work through it together. So the first step we must do in any geometry problem is draw a diagram, which hopefully you have done or have attempted to do. So here we are. So we have a triangle ABC. So we have A, B, C, and H is the orthocenter, so it's the intersection of these altitudes here. So there. So we have H here. So let's first look at gamma A. So this is the midpoint of BC, and we draw in the circle with radius this. So something like this. And this is A1 and A2. And we also have the similar points. So I'm going to draw this in red. So N, and then we have something like that. So that's B1 and B2. And I'll draw the last circle in blue. So this is point P, that's the midpoint of AB. And then we draw in this circle here. And this radius should also be marked. And if we draw this here, we get that. And that's C1 and C2. We have to prove that all these points are concyclic. So what can we do right now? Well, let's try focusing on proving that some of these points are concyclic, because proving that 6 points here are concyclic seems a bit hard and is a bit of a stretch. So for now, let's set a smaller goal and prove that B1, B2, C1, C2 are all concyclic. They all lie on the same circle. So what exactly happens if C1, C2, B1, B2 is cyclic? Well, if it were cyclic, then we end up drawing this circle here, which we know should pass through A1 and A2, but we'll ignore that for now. But we do have this extra circle here. And whenever we have these circles, this should remind us of radical axis. So if I complete the circle here and complete the circle here, we're tempted to use the radical center theorem on these circles. So if we use the radical center theorem, well, the radical axis of this blue circle and this black circle here is just C1 and C2 because it passes through C1 and C2. I should have probably made that more clear. Like this is the circle. So anyway, this radical axis is C1, C2, and that radical axis of the black and red circle is B1, B2. And this radical axis of the red circle and the blue circle here is some line passing through H. So by radical center, if this quadrilateral were cyclic, then A also must lie on the radical axis. And which makes sense because that just gives us the desired result by power of a point. Because if A lied on the radical axis, then AC1 times AC2 equals AB1 times AB2. I rephrase this in terms of the radical center theorem because I wanted to explain the motivation for using power of a point at A. All right, so let me go ahead and erase this big circle. So we want to prove that A lies on the radical axis of these two circles. And now let's see what we can do. We still haven't really used much info in the problem. We haven't even involved the orthocenter yet and the midpoints. So you want to somehow use the fact that this H is the orthocenter and these are the midpoints in order to prove that A lies on the radical axis. So if A lies on the radical axis, then that would mean the radical axis is just line AH. And that's your radical axis. And that involves a point H. Now we want to figure out how we're using the fact that P and N are both the centers. And that's when we realize that whenever we have the centers of these circles and we have the radical axis involved, the line through the centers is perpendicular to the radical axis actually, as I stated inside the radical axis theorem. When in our proof of radical axis, we discovered that the radical axis is actually perpendicular to the line through the centers. So if AH were actually perpendicular, if A was on the radical axis, then that means that AH must be perpendicular to the line NP. And we already know by definition that AH is perpendicular to line BC. So this is very, very promising. And so it really means that we want to prove that these two lines are parallel, given that N and P are the midpoints of these sides. But this is just true because N and P are the midpoints. And therefore, NP is parallel to BC because midpoints. Obviously, we can't rephrase our argument in terms of this. So we're going to be writing up the solution in a different way. The proof that B1, B2, C1, C2 is cyclic. So the first part is to go backwards. So we solve the problem by going backwards by first applying the radical center theorem to see what we have to prove, and then going backwards from there and getting a true statement, which is Pn parallel to Bc. So let's go forward. So we start with Pn parallel to Bc. And from Pn parallel to Bc, we see that Pn is perpendicular, to AH. But because H lies on the radical axis of these two circles, the red one and the blue one, this means that A lies on the rad axis. And therefore, by power of a point from A to the red and blue circles, we get AC1 times AC2 equals AB1 times AB2. And that means that B1, B2, C1, C2 is cyclic. And this should mean that we're done because B1, B2, C1, C2 cyclic, and similarly C1, C2, A1, A2 cyclic, and A1, A2, B1, B2 cyclic should imply that all 6 points are concyclic. Or at least we hope, right? Well, it turns out that it's slightly more complicated than that because we could have that every pair of 4 points is cyclic, but all 6 are not. For example, like if we have this like rectangular grid where this is like A1, A2, B1, B2, C1, C2, then A1, A2, B1, B2 is cyclic, as is B1, B2, C1, C2, and A1, C1, C2, A2. But all 6 points are not concyclic. So we have to use a different approach. And at this point, it feels like we're kind of stuck because what other approach could we take? Well, here's one approach that we could take. And this will feel a bit out of the blue, but one approach to proving that 3 circles are the same, we want to prove that B1, B2, C1, C2 circle is the same as a C1, C2, A1, A2 circle. So one way to prove that they're the same, given that they have C1 and C2, we just need to find one other point in common, or one other defining characteristic. And let's prove that they have the same center. So we know that the perpendicular bisector of A1, A2 must go through the center of the circle. So that means that the center of A1, A2, C1, C2 lies on this perpendicular bisector. And the center of C1, C2 of A1, A2, C1, C2 also lies on this perpendicular bisector. So therefore, the center of A1, A2, C1, C2 is just equal to the circumcenter O. But however, because this point O is symmetric, like it can just be taken on all sides, therefore, this is also a perpendicular bisector because the point O is symmetric. And this means that C1, C2, B1, B2 also has center O. So therefore, all 3 of these circles have the same center, and evidently, this forces all of them to be concyclic. And this finishes the problem. So there are a few things to take away from this problem. So one key lesson we took away from this problem is to work backward. We could have phrased the solution without appealing to radical axes at all, because we could have just introduced this intersection point here and just use a bit of perpendicular lines and just power of a point. However, the reason I included this as a radical axis exercise is because we can use a radical center theorem not only to prove important theorems, but also to go backwards. In this case, we went backwards by noting that we can just solve the problem by using power of a point at A, and noting that we have to prove that A lies on the radical axis. We turn that into AH perpendicular to NP, which follows by midlines, because NP is parallel to BC. And that's basically where the orthocenter gets introduced in this problem. And then the second lesson is to beware of configuration issues. Because if B1, B2, C1, C2 is cyclic, and similarly for the rest, then that does not imply that all 6 points are concyclic. We have to do another step. And this is one of the many solutions we could have taken. Another solution is to, if assuming that all 3 circles are distinct, is try using radical axis on all of them and see what you get. Like, try using radical center on B1, B2, C1, C2, and C1, C2, A1, A2, and A1, A2, B1, B2. Try using radical axes on all of these circles and use a radical center theorem. And if you get something weird, that means that you got a contradiction. And which means that all of them are concyclic. You'll be able to explore this idea further in one of the example problems I provided. All right, so go ahead and try out the exercises I gave in the handout attached to this video. I gave a plethora of exercises because radical axis is a very rich topic in math Olympiads. And radical axes are one of my favorite concepts in Olympiad geometry ever. So yeah, thank you so much for watching this video. I'll see you guys in the next one.